Perfect. So yeah, nice to virtually meet you all, and good afternoon. And thanks for the opportunity to present a little bit here our company SPACEOPTIX and our technology on the engineering and fabrication of metallic mirrors and telescopes for Earth observation from ultraviolet to infrared. So starting maybe with a background on the company, because we are not that old and probably not all of you have heard about us. So we are a spin-off from the Fraunhofer Society, more precisely from the Fraunhofer Institute of Applied Optics Precision Engineering in Jena, Germany. And we've been founded roughly 4 years ago with the goal to transfer the technology on engineering and machining of very high quality metallic optics, so components and systems from applied research to industrial production. So the push for that was clearly at this time the whole new space rush. So customers were asking for a serial production of optical mirrors, space-grade mirrors, and also optical systems, so telescopes, camera optics for Earth observation, optical communication. And we were 4 founders working for more than summarized 50 years on making metallic optics for space. So the idea was, okay, let's do that on a commercial way, spin off the company, go out from the Fraunhofer Institute. We started that business in an own fabrication site, so which is close to Jena. So every one of you who has been in Jena, Thuringia, right in the center of Germany. So we were 20 minutes west from that. We have a large fabrication site, roughly 3,000 square meters, and started 4 years ago to build up our own optomechanical workshop. So we installed a lot of equipment here, being able to produce this kind of metallic optics with CNC machining technology, diamond turning, diamond milling capabilities, polishing equipment, clean room, and a lot of metrology to measure these mirrors and to measure the optical systems that we do. We're coming from a scientific background. So before we founded the company, we were always working on metallic optics, mainly on scientific projects, on scientific missions, mostly one-off systems, very effortful, long-year projects, and we've been involved in several remote sensing projects, but also hyperspectral imaging, optical communication, interplanetary missions. A couple of them are listed here. So we've been involved, for example, in different Sentinel missions for ESA, and also on an altimeter for JUICE, so going to Jupiter. And it took us roughly 2 years to start a business, to get the equipment running, to have the floor ready, and then from 2022 roughly we're really able to now offer series production of metallic optics, so high-grade mirrors, mirror systems. We have nowadays produced roughly 3,000 mirrors, and we know that about 350 of them are in orbit. We don't know about all of them, but that's quite a cool number for this short time. And we're also introducing our own products since last year. So taking maybe the EPIC slides, the EPIC question already at this point, what can we offer to you? So what are our products and capabilities that we do? So we roughly have 3 lines. The one is that we just sell optics from stock. We call it stock optics. So that means standard mirrors, standard telescopes, but high quality. So like, for example, these off-axis parabolic mirrors that you see over here, we have a bunch of those optics available also on online platforms like Meet Optics. So it's roughly what you also get in the Thor Labs catalog, but on a higher quality in terms of surface form and surface roughness. So these are mainly nickel-coated mirrors, polished and figure corrected. So if you need such a mirror for a high-quality application. Second line is build-to-print manufacturing. So we do that a lot. If the customer comes and just has a finished product, a finished mirror, optical system, then we just build that from the technical data that we receive. This is an example of the 550 millimeter freeform optics that we did on one of our diamond turning machines. It's not for space, it's way too heavy, but it's for lab application. But it shows roughly the largest size that we can do. So we are limited to this 550 millimeters. So nice freeform optics manufactured here. And the third line is more regarding core engineering cooperation projects. So as we are coming from Fraunhofer, we're used to work in research projects and also in joint industrial consortia. So bringing our expertise from manufacturing into, for example, a system development. And this is an example here of a small sat payload that we develop in a consortium together with another company from Jena, Quantum Optics, and also the Fraunhofer Institute, 2 other companies, and under a DLR funding. And this is a small payload that should do entangled QKD from a CubeSat at one day. So I took 2 examples. I just have 2 more slides showing a little bit the capabilities where we could probably help the community with our technology. I divided that by wavelengths. So I took here a system that is more targeting the long wave infrared for another Fraunhofer spin-off, Constellar. They're located in Freiburg, Germany. They also founded roughly at our time 4 years ago, and they want to monitor the land surface temperature. So for agriculture from space in the long wave infrared. And in a joint project together with 2 Fraunhofer institutes and Constellar, we developed a small imaging payload, so a small TMA telescope that you can see over there, that was designed by the Fraunhofer Institute in Jena, and we took over the manufacturing of those of this instrument. And I hope you can see my mouse, and here it's integrated in a 3U platform, so roughly shoebox size, together with the detector and also the electronics here in the back. And the beauty of that is that it basically consists just out of 4 components. So we have 4 mirrors, 2 freeform mirrors, another aspheric mirror and plano mirror, and very precisely machined housing that you can see here in black. And the whole integration is actually done by the precision of the interfaces and the relative position of the optics to that interfaces. So actually everything is fixed by ultra precisely machined optics and interfaces. The integration of that telescope could be done within a couple of hours. So using this technology, you can simplify a lot of your system assembly tasks dramatically. And what we do offer here in terms of that infrared optics, actually we also co-engineer, so we take over a little bit of the system engineering, and then we offer the complete optics manufacturing, which is mainly CNC machining, thermal treatments of this special aluminum alloys, diamond turning, diamond machining, qualified cleaning, coating, and also system assembly. So we also measure the system performance, MTF, wavefront, and deliver to the customers the finally integrated telescope. Second example that I brought with me is a bit more effortful. So if we go to shorter wavelength applications like ultraviolet visible range, then usually the quality that we can achieve with diamond machining technologies is not good enough. So we need better surface form, better surface roughness results. And the standard way to achieve that is that you plate your optics in the most cases with a layer of electrous nickel. And this layer acts as an amorphous intermediate layer that can be diamond machined and polished and also figure corrected to very high qualities. And this is one of our standard technologies, also fully space qualified. I have a nice picture of a larger mirror over here. So this is also part of a hyperspectral imaging telescope. So it's the primary and the tertiary mirror of that telescope. You can see it's again machined on a common mechanical platform. So this is a special technology that we do so that we can already fix the relative position between those mirrors with the precision of the machine that we use actually. So you don't have to align them at the end. You see it's nickel plated, diamond turned and polished. And actually using that technology, we can achieve very similar results that we also could do on glassy optics or ceramic optics, with the advantage that at the end this is more tailored to mass production and to strongly freeform aspheric optics, also to cost-effective optics at the end. That's why this technology is so interesting for constellations nowadays. Maybe a word on the quality that is achievable. If we go with this functional layer and then adding polishing and figure correction technologies, then at the end, the surface form that we can achieve is more or less limited by the metrology that we have available for measuring the surface form. This is an example here down right, not of that mirror, but of a very extremely plano mirror that we did. So this is 85 millimeter aperture, and this was measured and figure corrected to surface form of about 1.5 nanometers RMS. So this is then more or less limited by the interferometer to measure the surface form. And with our polishing technology, also on the roughness side, on the small scales, we're working down to better than 0.2 nanometers RMS if needed. So this is roughness on a range of 170 by 170 microns. So what could we do for you here at this point? Again, system engineering, also complete optics manufacturing for short wavelengths operations. So CNC machining, diamond turning, plating of the optics, polishing, figure correction, and at the end also we integrate their telescopes and those systems delivered to the customer. We're only working on the passive part, so we're not dealing with detectors and not dealing with electronics. This is something that we would like to cooperate. This is then what do we need from the EPIC members. And with that, I would like to thank you for your interest, and I'm happy to take questions.